Dear students, let us continue our learning the course System Software and Compilers. This is the second session of the first topic of the module 5. The topics covered under this session are from the syntax directed translation, that is evaluation orders for syntax directed definitions. Myself, Dr. SURESH.D from the Department of Computer Science and Engineering of Canara Engineering College, Bantwal, Mangaluru. In the last class, we learned how to construct the annotated parse tree for L attributed SDD and the S attributed SDD. Let us continue with it and let us learn how the evaluation orders for the SDD will work. For defining the evaluation orders for the SDD, we are going to use dependency graphs are used over there. So dependency graphs are the tools for determining an evaluation order for the attribute instances in a given parse tree. So wherein the annotated parse tree will show the values for the attributes, the dependency graphs helps us to determine how those values are calculated. In the annotated parse tree, we get the values. Dependency graphs will tell us how these values we are going to obtain, how we are going to get those values. Fine. It is a graphical representation of the flow of the data. How we are going to obtain these values. The flow of the data is depicted through the help of the dependency graph. That is, if you go with the formal definition of the dependency graph depicts the flow of information among the attributes instances in a particular parse tree. That is, an edge from one attribute instance to another means the value of the first is needed to compute the second one. That is, if I have a attribute, if I have a arrow as a dot a, x dot a, y dot b, the meaning is that to calculate the y dot b, I need the value of x. I need the value of x dot a. I need the value of x dot a. That is, this has to be solved first before I could solve this one. That is the meaning. That will be given with the help of the dependency graph. That will be given with the dependency graph. That is, dependency graph depicts the flow of information among the attribute instances in a particular parse tree. That is, in edge from one attribute instance to another means the value of the first is needed to calculate the second one. The value of the first is needed to calculate the second one over there. Fine. So now, let us go with the construction of the dependency graph. Now, if you observe over here, it is of the same grammar. Fine. That is, E derives E plus T. Fine. So how we write the parse tree over there? E derives E plus T will be written like this. E derives E plus T. So this is our parse tree. Fine. So this is our parse tree. So now in the dependency graph, now we will write the dotted parse tree over there. Now how we calculate the values? E dot val. So this will be E dot val. This will be T dot val. So now to get this E dot val, I need the values of the E dot val and the T dot val. So now this will be your dependency graph. That is, dependency graph will tell us how we will get the values. How we are going to get the values over there. Right? Parse tree is the construction of how we get the tree. How we will get the input tree over there, wherein the dependency graph will tell us how we are going to get those values. The dependency graph is constructed for both S attributed as well as the L attributed definitions. It is constructed for both the S attributed and the L attributed definitions. Now you observe over here. Right? So how we get those values earlier and how we are getting over here, you can observe over here. Right? So it is a dependency graph for the multiplication over there, that is a 3 star 5. It is for the 3 star 5. How was the graph over there? T derives F T dash. The parse tree was T derives F T dash. Then F derives digit. F derives digit. And T dash derives T dash derives star F T dash, then F derives digit and F derives digit and T dash derives epsilon. So now this was our parse tree. How was the annotated parse tree? Was a digit dot lexval. Digit dot lexval will be equal to 3. So now this will be given to the F dot val will be equal to now 3. This was synthesized attribute. So now in the inherited attribute, T dash dot inherited value will be equal to 3. So again this value, this will be digit dot lexval was 5. Digit dot lexval was 5. So now this will be given to the F as a synthesized attribute. F dot value will be equal to 5. Now to get the T dash dot inherited value, it will be equal to T dash dot inherited value multiplied with F dot value, which was 15. So now once it becomes epsilon, this is our synthesized value. T dash dot synthesized will be equal to 15. So now this synthesized value was passed over here. That is T dash dot synthesized value was 15. So now this will be passed to the root as a T dot val, which will be equal to 15. So this was our annotated parse tree. Now how we get those values? The dependency graph will give us the way with which we will get the values. Now you can observe over here. First we take the value from this one and we will pass over here. Fine. So that is the first one. That is the value from digit is passed over here. That value is passed as a inherited value. This is passed as a inherited value. This is passed as a inherited value. So next this digit value is passed. Digit value is passed. And these two are passed as the inherited value. These two are passed as the inherited value. Then next, once it becomes epsilon, this value will become the synthesized value. Fine, that 15 was becoming the synthesized value. That value is passed as a synthesized value. That is passed as a value. That is, this dependency graph will give us the flow. How we are obtaining those values. How we are getting those values. The flow will be given with the help of the dependency graph. The dependency graph will give us the flow of the data, how we are going to get those values in the annotated parse tree. How we are going to get those values in the annotated parse tree will be given with the help of the dependency graph. So dependency graph is a graphical representation of constructing the annotated parse tree. Fine. Now if we continue, fine. So now once we are able to construct the dependency graph, now we should be able to write the ordering in which order we need to solve the values for the attribute. In which order we need to solve the values for the attributes. Fine. So now for this one, normally we come across the word topological sorting. For the finding the evaluation order of the S attributed or the L attributed definitions, we construct the topological sorting. So topological sorting means it will be constructed like this. X, A, if it is constructed like this, so means to get the value for the X, I need the A, right? That is A to be written first, then the X. Suppose I need to get the B also over there. Fine. Then first I need to calculate the value of the A, then the B, then the X. That ordering will be your topological sorting. That is in any directed graph. So topological sorting is not constructed for the cycles, remember. It should be free from the cycles. Right? This topological sorting will tell us which is to be solved and which are dependent on it. So once the dependents are solved, only then you can solve the value for the node. Once you can solve the dependents, then you can solve the value for the node. Fine. That is, if to get the value for the nj, I need to solve the value of the ni. Means ni will be written first, then the nj will be written. If ni value is needed in the nj, then in the topological sorting we will write the ni first, then the nj. Fine. So preferably the topological sorting should be free from the cycle. If there is a cycle, means you can't have the topological sorting. If you have a cycle, then you can't have the topological sorting. So now topological sorting is applied. Yes, I agree. Fine. Then next will be, then what about the S attributed definitions? For the S, so if we go for constructing the topological sorting for the previous one, in this one, So this is the order. This is the order. Let me erase it. So this was the order. So now let me solve it. So first, to get the value of the 3, I need the 1. So 1 will be written first. Then next 3 is dependent on the 1. I can write. Then next one, it is passed to the 5. This is passed to the 5. Again, the value of the 2. Then it is needed in the 4. Next I will get the 6. 6, we need the values of the 5 and the 4. 5 and the 4 both are done, then the 6. Then next step is 7. Then next step is 8. Then next step is 9. So this is the order in which you have to solve to get your result. This is the order in which you have to solve to get the result. So this is your topological sorting. So this is your topological sorting for the L attributed SDD. For the L attributed SDD, this is your topological sorting. Fine. So then next, what about the S attributed SDD? So S attributed SDD is quite simple. You just go with the post order notation I was discussing. So what is S attributed? All the attributes are synthesized. All the attributes are synthesized means what? The root will come only after the solving the children. The value of the root will be computed only after solving the values for the children. That was your S attributed definition. Fine. So now if I just follow the post order notation, if I go for evaluating the post order notation, then I have my evaluation order for the S attributed SDD. Fine. That is, if you merely follow the post order notation, you have your values. Fine. So that will be regarding your S attributed. L attributed definitions. L attributed definitions first. L attributed is having both the categories over there. It is having both the inherited attribute as well as the synthesized attribute. Synthesized means what? The values of the node we obtain only after getting the values of the children. Inherited attribute, the node value is dependent on its root as well as its left sibling. Fine. So that is your L attribute definition. That is, it can have both the synthesized as well as the inherited attributes over there. Fine. Fine. So now if you observe, T derives F T dash. So T dash inherited value is dependent on the F. Fine. So this is your inherited attribute. Then the T dash derives star F T dash. This value is dependent on one, it will take it from the T dash, other it will take it from the F for the multiplication. That is your inherited attribute. Fine. That is, in all the cases of your L attribute, inherited means it can take the value from its sibling and the root. But to be an L attributed SDD, the sibling should be on the left side. It can't take the value from the right side. It can't take the value from the right side. Fine. So now if you observe over here, B, it is taking the value from the A as well as the C. Now it is not L attributed because C is not on the left side, it is on the right side. So B is the right side sibling of the B, so which is not allowed. We should have the C can take the value from the B, but B can't take the value from the C. Fine. That's why any SDD where rule cannot be L attributed, means L attributed definitions means I should get the values from the left side sibling, not the right side sibling. Fine. That is, the first one is legally correct. That is, A synthesized attribute it is getting from the B. It's well and good. But the second one, the second rule in which it is not a S attributed. Fine. So in this one, what happens? The SDD cannot be L attributed because attribute C is used to help the value of the B. But C is on the right side. But C was on the right side, because of which we are not able to construct. Right? Now this is not an L attributed definition because we are getting the value for the B from the C, which is not allowed in the L attributed. In the L attributed, even though the values are inherited, but you can inherit only from your left side sibling, not from the right side sibling. That you have to be careful. Right? Then the next one, semantic rules with the controlled side effects. The best example for this one will be your desktop calculator, what you designed in the lab program. That is your $1 plus $3. That is the best example over there. Fine. So that is a desktop calculator might print a value of the result. Fine. That is whenever, that is a side effect means what? You have a rule and you are going to work on it. That is a rule along with its action. So rule along with its action, we are going to have it as a controlled side effects over there. Fine. Let us take one example now. Fine. So that is here, this is our rule. L derives En. What was our action part over there? Print the value of the E. This is our side effect. So here what happens now, whenever I get the rule, I am going to print. This is once I match that rule, that action will be executed. That action will be executed over there. That is, it will permit the accidental side effects that do not constrain the attribute evaluation. Here we are not evaluating anything, we are printing the values. Fine, so we are not evaluating, we are printing the values. That is, whenever these are our side effects over there, when we get this one, this will be get printed. This will be get printed. That we will call it as the controlled side effects over there. Fine. So now let us take up the next example over there. Next example for the declaration. First, D derives TL. T derives TL. Let me take up the example as int A comma B comma C. Let me take this example. Fine. So now A is of type. So A can have any value, but what is the data type for the A? A is of type integer. Integer is on which side? Integer is on the left side. So which type of attribute it is? It is an inherited attribute. It is an inherited attribute. Fine. That is then B. B is of type which type? It is of the type A. B is of the type A over there. It's an inherited attribute. C is of which type? C is of type B over there. It's an inherited attribute. They are taking their values from the left side sibling. They are taking the values from the left side sibling. It's a very good example for your L attributed SDD. It's a very good example for the L attributed SDD. That is your declarative statement. The same thing when it is expressed as a grammar, how it will be, let us look. First, declarative statement. D derives data type followed by the variable list. Declarative statement, that is, it is an example for the declarative statement, whole thing. It is first will be your data type, that was our T. Then next is the variable list, that was our L. T can be integer or the floating point number. T can be an integer or the floating point number. Then L can be any list of the integer with a minimum of one identifier over there. Any list of the identifier with a minimum of 1. Fine. So now let us look how the inherited attribute will work over there. First, L variable. What is the data type for that variable, which is on the left side over there? That is L dot inherited value will be equal to T dot type. L dot inherited value will be equal to T dot type. Then what is the T dot type? If it is integer, then it is integer 1. If it is a float, then it is a floating point 1. Next case, L1 comma ID. How it will be? Fine. First one. Here, let us take the A comma B. Now for this one ID, I will store it. That is the inherited value. That is the type. Then this L1 will inherit the value from the L. L1 is inheriting this one. L is inheriting the value from the T. L is inheriting the value from the T. L1 is inheriting the value from its root. What is the root over there? L. That is L is giving the value over there, the inherited value. Now the inherited value L1 dot inherited will be L dot inherited, and ID will take up the value of the inherited value over there. Fine. Then whenever L derives ID, then we are storing that identifier along with the type to the table. Along with type to the table. Fine. So it is a simple example for your L attributed definitions. That is your variable declarations. Fine. Now let us look at the example over here. That is a float ID1 comma ID2 comma ID3. So if we write the path tree for this one, how it will be? D derives TL. D derives TL. T is of type float. T is of type float. Then L derives L comma ID. Again L derives L comma L derives L comma ID. Then L derives ID. First one, float, it is passed to the T over here. T dot value you can observe over here. T derives float, then T dot type will be equal to float. That is the value of the is passed over here. Then next, D derives TL. The type is passed to the L. What is the type over there? Float. As the inherited value it is passed. Then L derives L comma ID. Again it is passed over here, along with adding the value to the symbol table. Then again it is passed over here. Then here we will add the value to the symbol table. And now you can observe. So here this is passed value here. That is a type. That is float. Here it is pass. here it will pass. ID, comma, ID, comma, ID. Right? So then these entries will be made to the symbol table. That is, from root we are passing the value. From the sibling and the root we are passing the value over here. It is an example for your L attributed definitions. So this is the dependency graph. How the values it is flowing over here. This is your dependency graph. That is, it is taking the value from here, then here, then here. Along with that one, it is passing the value. We are making the entry to the symbol table. We are making the entry to the symbol table. Right? And the next example. Then the next. Then this is how we construct the values for the floating point of ID, ID1, ID2, ID3. Fine. And next is the exercise part. Fine. So now the next one we will continue in the next video session. So in this session we learned the evaluation order for the SDDs for both the L attributed SDD as well as the S attributed SDD. This will be done with the help of the topological sorting. That is, dependency graph is constructed and we will have the topological sort. For the S attributed SDD, just having the post order is enough over there. The references for this presentation are taken from the textbook Alfred Vivo, Monica S. Lem, Ravi Sethi, Jeffrey D. Ullman. The textbook is Compilers, Principles, Techniques and the Tools. It's in Pearson publication, 2nd edition, 2007.